Hello everybody. In the earlier video about aromatic nature, we have introduced you some interesting cases wherein we came to the conclusion to explain the extraordinary stability of the aromatic systems. A simple resonance theory is insufficient because if it is a question of delocalization, how do you account for the fact that cyclobutadiene is so unstable? Therefore, to account for the extraordinary stability of cyclic conjugated systems, we require a new approach. It does not mean we are discarding valence bond theory. We do retain that for its obvious advantages of simplicity of representation. Otherwise, we must follow a new tool, new route, and this route to know more details, having more insight into the molecular structure, is called as molecular orbital theory. Molecular orbital theory, abbreviated as MOT. Here the focus is on molecular orbitals. Please remember that point here. Therefore, we are postponing about electrons which are likely to be accommodated in orbitals and focus only on the molecular orbitals. Remember, when a molecule is formed by combination of atoms, what we are getting is one unit. Therefore, orbitals over them, which are aptly called as molecular orbitals, belong to the entire molecule, not belong to particular atoms they know. The orbitals or molecule is a property of the entire molecule. If that is the case, the question of what's called delocalization becomes much easier to understand because it's the entire thing belongs to the entire molecule, all molecular orbitals. So, we are starting with an advantage, which is coming very naturally as part of this theory. Now, if I say molecular orbitals, the first thing that comes to mind is in a molecule, whatever the simplicity or complexity of that, how many orbitals are there? Here we are governed by one rule position called as a linear combination of atomic orbitals. The focus, as I told you, is in molecular orbitals. The question that we are raising is how many molecular orbitals are present over a molecule. And we follow a rule position called as linear combination of atomic orbitals. Of course, the idea is not to discuss about molecular orbitals at this stage, but use it to the extent to understand the extra stability of benzene or no stability for a molecule like cyclobutadiene. That is the main agenda now. But we do require some preliminary, some working knowledge of molecular orbital theory. Now, how many molecular orbitals? In that case, a simple thing to remember is, suppose if I am combining two hydrogens to form H2, this is the molecule and these are the atoms. Therefore, I have one atomic orbital, I should get identical number of molecular orbitals. The simple example about hydrogen I have invoked because the number of molecular orbitals over a molecule must necessarily be equal to number of atomic orbitals. Suppose if I am taking this example, you can easily see that. Even if I am taking simple molecule helium plus helium, there also only one atomic orbital. Therefore, number of molecular orbitals over helium molecule, if formed, should be 2 MOs only. We should keep that point in mind. Therefore, any molecule must have identical number of molecular orbitals as that of the participating atomic orbitals. Now, in the case of benzene, the focus is not on sigma bonds because the stability is not with reference to that I am talking. The stability is with reference to the ring current. So, how many atomic orbitals are there? In the benzene structure, if you remember it, perpendicular to the planar CH skeletal framework, there is a p orbital in each of the carbons. There are 6 carbons, therefore we have 6 atomic orbitals. Therefore, I have expected 6 molecular orbitals which will accommodate these electrons called as pi electrons. 6 atomic orbitals. Therefore, my focus is on benzene again. The formula, as you are aware of, is C6H6. This is my hexagon. I am not writing details about carbon and hydrogen. My focus is on the orbitals, p orbitals. On each of the carbons, I am having one p orbital, which is unhybridized. And I want to combine the six atomic orbitals on carbon atom and form molecular orbitals. So as stated earlier, we should be landing up with this combination of six atomic orbitals over carbon to form six molecular orbitals. So how do we construct six molecular orbitals? As I told you, the focus is on molecular orbitals only. Later on, electrons will come after a few minutes. So, to generate six molecular orbitals, how do I proceed now? See, the mind is totally involved only in the valence bond theory. Therefore, we say it was easy for us, and we are having what's called total view colored by valence bond theory. Now there is a paradigm shift. Our molecular orbitals are spread over the entire molecule. Entire molecule. To achieve this, we must realize we must invoke wave character of electron. Wave character of electron. There is a definite shift here. Please remember that point here. If you remember, De Broglie was the first person who has given a fictitious wave character to an electron. Therefore, I am considering electron as wave. Now, where is this electron right now, situated right now? In the atomic orbital, that is the orbital. Now, I am forming orbitals, is it not? Therefore, I must think in terms of the orbitals, not with reference to as we have done earlier. Now, I am invoking wave character of electron here. That is, if I take an electron, it is in the form of a wave. Wave can easily be visualized into something like this. And there are identifiable portions. This is called as crust and this is called as trough, if you remember this point. And if you stand in front of any water body, you can see that easily. Suppose if you are standing in front of a seashore, sometimes you can see the waves are getting enhanced. They are bigger. And sometimes the waves that you are getting are in the form of ripples or maybe a flat line. That means when number of waves are traveling together, they start interfering with each other. This phenomena is correctly called as interference. Suppose imagine number of waves which are traveling towards the shore, if they are moving in synchronized way, that is the crest portions are together and trough portions are together, and this is the area of electron density. Remember that point? So if all the crests are moving together, we realize the height of that will increase. Height may refer to this or this one, both are identical here. Height increases, that means there is an enhanced electron density whenever there is a constructive interference. Suppose on the contrary, we do not have that kind of constructive interference. This is the peak portion, the crest portion, this is the trough portion. If they combine, the interference is destructive interference. They destroy both the peak portion and that becomes flat. Flat means what? The electron density is 0. You remember the word for that you must be acquainted by this time, node. Nodal point or nodal plane, which means the electron density is nearly 0. Therefore, my interference of waves can lead to a constructive one or a destructive one. And depending upon that, we are getting molecular orbitals which are good enough to accommodate electron density to the maximum, maybe slightly less. Maybe ultimately we have a situation where electron density could be 0 also in a molecular orbital. Therefore, I have to think like this. I am having 6 waves corresponding to 6 atomic orbitals. Is it not? Now they are moving now. I want to construct molecular orbitals from the 6 atomic orbitals. These are the 6 atomic orbitals I am talking. And I am constructing like this. 1 wave, 2 waves at least I will construct out of the 6. Because as I told you, we must get some working knowledge about this molecular orbital theory such that we can understand about the stability of benzene or non-stability of cyclobutadiene. So here what I am doing is, if all the 6 orbitals, they are moving synchronized, that means I will have a wave which looks like this. This entire thing is electron density. There is no place where we can say there is no electron. Everywhere there is an electron here. And in that case, the nuclei that are there, whatever that means to us, I think they are having tremendous attraction towards them. That means if there is a lot of attraction with the electron density, which is full here, 7%, and both the nuclei are attracting each other, that will be highly stable arrangement for electrons, and therefore the energy of that particular orbital is least. On the contrary, imagine I have taken another extreme case where I am likely to have only destructive interference. That means I don't think any peak portion is observed. Entire thing is becoming flat. The entire thing is of nodal plane only. That means between two nuclei, I do not see any nuclei. If I do any electron, please. Between two nuclei, if I don't see any electrons, what does it mean? The nuclei start repelling each other. In that case, the energy of that particular molecular orbital is the highest. I am having two sets of orbitals, isn't it? One least energy, other highest energy. And we are left out with four more molecular orbitals. And I will tell you only one point here, and I will tell you how do we try to appreciate that point here. And these four orbitals, we arrange them in two sets, degenerate sets. Out of them, one set will be of lower energy, other will be higher energy. Compared to what? Compared to the energy of the atomic orbitals. Therefore, if this is the energy of the atomic orbital here, the least one is my, what I was talking, only constructive interference, and the maximum is only destructive interference. And here I am having here two orbitals which are degenerate, lower than average energy, and two more above this one here. So it all depends upon how many nodal points we are having here and what is their symmetry. Therefore, I am likely to have a situation for benzene like this. Therefore, below the average energy, I am having two sets of orbitals. One is single and other is degenerate. Now, how many electrons are there? Now come to electrons here now. Electrons, remember, once the slots or the orbitals are ready, then we have to accommodate electrons into the orbitals. Remember, while we are accommodating electrons into the orbitals, we do not have any extra special rules. Whatever rules that we had in mind while accommodating electrons in atomic orbitals, I think same set of rules are followed here. Like what are the same set of rules, please? You remember Hofbauer rules, electrons are arranged from least energy to maximum. And no two electrons can have four quantum numbers same. That is our Pauli's exclusion principle. And if they happen to be degenerate, we follow what is called as Hund's rule of maximum multiplicity. Therefore, the same set of rules we are following here. So, I want to keep this in mind and try to understand about benzene and also cyclobutadiene molecules here. Now, I am not really deriving anything here, but we follow a rule of convenience called as polygon rule. What is this polygon rule I am referring to? Polygon rule. P-O-L-Y-G-O-N. Briefly, polygon is a geometry. So, what is the geometry of benzene molecule? It looks like hexane only, is it not? So, we draw that. And what is the geometry of cyclobutadiene? It looks like diamond, for example. We draw that. Then, the way we are drawing indicate there are some apex portions and some portion in the middle. Let us try with benzene molecule. I will draw the hexagon first. I am not drawing benzene, I am drawing hexagon only here. So, this is my hexagon. This is my hexagon. And this, wherever there are meeting points here, that is the location of the molecular orbital. And I draw one line which cuts this into identical halves. Incidentally, it is cutting like this in the case of benzene. This is the energy of the atomic orbital. Energy of the atomic orbital. Therefore, some of the molecular orbitals are lowered in energy and some molecular orbitals are going up in energy. Therefore, this is the orbital. This is drawn with reference to energy. So, this orbital has the least energy and this orbital has the maximum energy, and these two orbitals are degenerate but definitely lower in energy compared to the average of the atomic orbital energy and higher than this, and two more are coming here. This is the orbital picture of benzene. Now come to electrons, please. How many electrons are there? Only 6, is it not? Each one per p orbital we have only 1 here. Therefore, these 6 electrons I want to accommodate now. 2 will go here as per the Hofbauer principle over and we are left out with 4 more out of 6. Because they happen to be degenerate, I should arrange this one here, one here. We are following Hund's rule, and one more electron here and one more electron here. That completes the quota. That means if you watch out carefully, we have filled the electrons only in the bonding level. Bonding level. All these orbitals, these MOs, they are called as bonding molecular orbitals. Are all of them completed? Yes. And this high energy one, they are called as ABMO, which otherwise means anti-bonding molecular orbitals, and they are weakened. Whenever you have a molecule where electrons are completely filled in the BMO level and none in ABMO level, you must understand that particular molecule is highly stable. Let me give you one more good example. One of the inert substances, stable substances we have in the environment surrounding is nitrogen, N2 molecule. N2 molecule. Of course, I'm not drawing the diagram now, but only one point I should talk from nitrogen molecule is all the electrons are in the bonding level and there are no electrons in the anti-bonding level for that. I repeat, electrons are only in bonding level, none in anti-bonding. Whenever such a thing happens, it will be a very strong bond. In fact, nitrogen bond order is 3, indicating it is very, very stable. Higher the bond order, more is the stability. Therefore, nitrogen is extremely stable because of the one situation, electrons are bonding completed and no electron is there in the antibonding level. Extremely stable. Therefore, benzene, in terms of molecular orbital theory, we can clearly make out why it is so stable. Of course, the working definition, conjugated, cyclic, everything, let it remain. But for the cyclic conjugated compound, this is the MO diagram I am drawing. And as per this MO diagram, benzene has electrons in that sextet, which is normally called as aromatic sextet, which is highly stable. That is the reason these electrons are not lost on its own under ordinary conditions. If at all, if there is some electron adding electron lost here, it is only as part of a transition state, but it is not a ground state property of benzene. Hope you are understanding why this is stable molecule benzene. So cyclic conjugated, this is the ultimate diagram, bond energy diagram that I am here, molecular orbital diagram I am getting here. Now let us talk about cyclobutadiene. Cyclobutadiene is also cyclic, conjugated, etc. So I wish to draw now a polygon for cyclobutadiene. This is the energy axis I am taking here, and this is how it looks like. This is the shape of the cyclobutadiene as well. I am drawing this as a diamond shape. Therefore, I have an apex, that's how we draw. There is one portion, and there is one more, and there is one more. 4 orbitals, 4 molecular orbitals, because 4 atomic orbitals are involved. Remember that this was the original valence bond diagram for our molecule. This, in terms of MO diagram, it looks like this. And therefore, this is the least energy. Therefore, and remember, my average cuts through the center of this, unlike benzene. I am having out of the 4 electrons in cyclobutadiene, 2 are coming here, excellent. 2 more are left out and they are degenerate here. Therefore, 1 electron here and 1 electron here. It has a diradical. How do you expect a diradical to be stable? They have temptation to undergo dimerization, is it not? That too in the Diels-Alder dimerization that I was referring to in the earlier session. It's very swift reaction. Therefore, this is not having lower energy, first point. It is not a stable molecule. I'm getting that point. Therefore, the cyclic conjugated system, stable or unstable, you can decide only in terms of MO theory, please. Lastly, I want to tell you, therefore, this I'm not drawing for cyclooctatetraene because the question of delocalization is not there, not a strong point because it's a top shape. The planarity is not there in cyclobutadiene. Therefore, we are not talking about that now. Only these 2 molecules I am talking with reference to MO theory to understand. What about the cyclic conjugate system? So if this is not at all stable, I don't think we should call that as aromatic. In fact, it is exactly anti-aromatic. Anti-aromatic this. Therefore, to summarize at this stage, I want to draw, imagine, this is my benzene molecule, aromatic, and I want to compare this with one more molecule like this. Imagine there is a bond like this. This is not cyclic. Therefore, this is cyclic and aromatic. This is many times stable than this is other compared to system here. Or if I am drawing, this is more stable. Suppose if I am drawing now my cyclobutadiene, and this is much less stable than ordinary molecule. This is less stable, and this is aromatic. This first molecule is aromatic, and the second case is anti-aromatic, and the third case is, suppose if I am drawing a molecule like this. Third molecule, try to follow. The third molecule is like this. I don't think it's aromatic. I have only drawn two bonds here. And this was somewhat comparable to what's called ordinary molecule draw. So this is neither coming an anti-aromatic or aromatic. This is called as a non-aromatic. Or still better term for this is aliphatic. This is aliphatic molecule. Hope this point is clear. Now what we have to do is we have to quantify this understanding about electrons, some specified number of electrons and particular orbitals they are occupying, imparting stability. That we'll do in the next video. Thank you very much.